welcome back. We're now in section 5.2 going to start working on the definite integral and trying to tie in this Riemann sum perspective to what we call the integral or antiderivative, as you would have remembered from section 4.9 from the Calculus 1 course. So we're tying all this stuff in on what you guys had before in that last few sections of calculus, which was talking about the antiderivative. So here's our definition. Definition of definite integral. That this integral, or antiderivative, integral from a to b of f of x dx is equal to the limit as n approaches infinity of the sum as I goes from 1 to n of f of xi delta x, where delta x is equal to b minus a over n, and xi is equal to a plus I times delta x. Now you look at this and go, wow, this is getting quite deep. Oh, but not really. We're trying to make it easier for you guys. You know, we had to use that definition of derivative in the old days before we taught you the easy way of taking the derivative. Well, this is kind of the same idea. N was the number of partitions. And the better your approximate area under the curve is of that Riemann sum, is the more partitions you have, the better the approximation is going to be. And if we can take it to the extreme, the number of partitions can go to infinity. An infinite number of partitions, the error would drop off to be 0, and this Riemann sum actually becomes this antiderivative integral from a to b of f of x dx. And again, remind you from a geometric perspective, this is the area under the curve. So an example here is if we wanted to find the area under the curve of the function f of x equals 5x squared plus 1 on the interval between 0 and 2. Well, there's two different ways we can write this. You can write it the Riemann sum way, or you can write it the integral way. The integral way is very straightforward. To find the area under the curve of a particular function, it is the integral over the bounds between 0 and 2. So you would read this, the integral from 0 to 2 of the function. Our function is 5x squared plus 1 dx. That tells you what the variable is. I mean, it stands for with respect to x. But from the Riemann sum perspective, this would be the limit as n approaches infinity of the sum as I goes from 1 to n of 5xi, replacing x with xi, squared plus 1, plugging xi in for x, times delta x. And this is the Riemann sum formula. This is the integral formula. This is the exact same thing. Okay? So we're going to get used to that notation. So look at this example here. It says this, approximate using the midpoint rule. We've done left, right, and midpoint rule Riemann sums. This time they want me to use the midpoint rule Riemann sum with n equals 3 of the subintervals is used to approximate the integral from 1 to 7 of the natural log of x dx, and we're going to round our answer off to 4 decimal places. All right, so they are writing it as an integral, but they're asking me to calculate this guy as a Riemann sum. So I have to identify the function. F of x is going to be the guy on the inside. That'll be the natural log of x. My bounds or my regions, a to b, is that interval. So my a and b would be from 1 to 7. So a is equal to 1, b equals 7. And they're telling me what n is. N is equal to 3. So what they're asking me to do is do a midpoint Riemann sum. And when I do a midpoint Riemann sum, I always draw this thing out. I'm trying to graph it between 1 and 7 on the x-axis. So here's 1. Here's 7. The partition is 3, so I need to calculate my delta x. Well, hopefully you got this formula memorized by now. It is b minus a divided by n. That'll be 7 minus 1 divided by 3. 6 divided by 3, and 6 divided by 3 is 2. Delta x equals 2. So we're starting at 1, and my width of my partition is going to be 2. So 1 plus 2 makes it 3. And actually 3 would be more in the middle there. Thank you, John. Okay, 3. And 3 plus 2 equals, say, 7 minus 1 is 6 divided by 3 is 2. Delta x is 2. So we need to calculate every 2 units. 1, 2, 3, 4, 5, 6, 7. So let me actually put hash mark in here. 1, 2, 3, 4, 5. This would be better if I wrote it evenly. 6, 7. That would be better. So you guys can read this thing. Alright, so 1, 2, 3, 4, 5, 6, 7. Here we go. Delta x is equal to 2. So starting at 1, and I moved 2 over. So here's 2. So I get 3. Delta x equals 2. And then my next partition, move 2 over from 3. 2 over from 3 is 5, so there's another delta x equals 2. So 5 would be by into my next partition. And then 2 more over from 5, delta x equals 2, gives me to that nice endpoint of 7. And here's my function when I graph a natural log of x, we know it decreases. It looks like that. Now, these are the endpoints of your partition. But they wanted me to do the midpoint. So if I draw these guys out, these partitions here, 1, 2, 3, 3 partitions, so I know I'm on the right track now. But we wanted midpoint. Midpoint, we have to use the point in between the endpoints. Between 1 and 3, the number is 2. Between 3 and 5, the number is 4. Then between 5 and 7, the midpoint is 6. It's still a Riemann sum, so this integral from 1 to 7 of the natural log of x delta x is going to be equal to, or approximate, we'll use the squiggly equal to, this Riemann sum of f of xi times delta x, again using midpoints. So this would be equal to, using midpoints, would be f of my midpoint 2 times delta x plus f of my midpoint, my next partition, which is 4 times delta x plus f of my midpoint, which is 6 times delta x. Well, what's my functional value? F of 2. Well, my function, right from the get-go, is the natural log of x. So the natural log of 2 would be my functional value. We will be using a calculator in a minute. Times delta x, and when we calculated delta x, this time we got 2 plus f of 4, that'll be the natural log of 4, times delta x, which is 2, plus f of 6, which would be the natural log of 6, times delta x, which is 2. So now I'm going to grab the old handy-dandy calculator, because they wanted me to approximate this to 4 decimal places anyway. So this would be the natural log of 2 times 2 plus the natural log, parentheses there, natural log of 4 times 2 plus the natural log of 6 times 2, and I end up getting the number 7.742402022. And to answer any kind of interesting web work question that we're kind of throwing at you guys on this stuff, they want it to 4 decimal places. So my answer would be, for 4 decimal places, 7.7424, 4 decimal places. So, but what they're really after on this particular section is the ability to go backwards and forwards from the integral to the Riemann sum, and from the Riemann sum back to the integral. And then we're going to be talking about what exactly are we doing. We're still doing the same old, approximating the area under the curve. Now, if you'll notice that using the midpoint Riemann sum is a little better approximation, and the reason why that is because versus the left versus right Riemann sum is when you use the midpoint, you know, your left part will be maybe over or under, and the right part will be over or under, and the goal is some of this error is canceling out, so you get a better approximation to the actual area under the curve. Remember, the integral is the exact area under the curve. Well, I'll look at the next one. So, they're really getting, this whole section is about getting you guys into the integral notation. Okay? Evaluate the integral. Integral from -2 to 4 of 2x minus 4 dx. By sketching a graph. This is by, in other words, using geometry. Okay, and finding an area. So you're actually not supposed to calculate these things. We're going to teach you guys how to calculate integrals very, very shortly. But right now, they're going to big into drumming it into your heads, this whole idea of area under the curve. So on this particular one, we want to graph it. We're going to graph between -2 and 4. This time I'm actually putting my hash marks evenly on this guy here, and we're going to be graphing. And all I care about is between -2 and 4. So let's see here. If I plug in -2 into this thing, now my function is what you're integrating, which is 2x minus 4. Okay? So if I plug in -2, 2 times -2 is -4, minus -4 is -8. So down here, we'll make a mark, -8, we'll mark there. Okay? Now, if we graph like 2, I'm going to plug in 2 because it's nice. 2 times 2 is 4, minus 4 is 0. It actually crosses the x-axis right there. That's kind of sweet. And now if we plug in 4 into this thing, 2 times 4 is 8, minus 4 is 4, so I think it's about there. And you notice 2x minus 4 is the equation of a line. So all I really needed was 2 points there, so there's my line. Keeps on going either way. But now here's the deal. We want you to integrate this guy. We're drumming it in your head. When you integrate a function, you're calculating the area between the curve back to the x-axis. So here's my curve. So back to the x-axis, so there's this area over here. And between the curve and back to the x-axis, there's this area here. Now the big deal on this one is, this area is captured below the x-axis. This area is above the x-axis. Area captured between the function back up to the x-axis or below the x-axis is called negative area. And what area captured above the x-axis is positive area. So they'll end up canceling each other out. But again, we're supposed to use geometry. So this is the integral from between -2 and 4 of 2x minus 4 dx. That's going to be equal to, well, the area. It's a triangle. An area of a triangle, area, is 1/2 base times height. Alright, so what's my base here? The base is how many units? 1, 2, 3, 4. The base is 4. The height is, how high is this thing? It goes from 0 all the way up to 8. It's 8 tall. Okay, but it's area below. Notice the negative 8 thing here. It's area below, so we know this is going to be 1/2 base times height, and you're going to have to make this part negative. So this is the negative area. Plus, this is positive area. So it'll be 1/2 base times height. The base on this particular little triangle is 2 units. The height is 4 units, looking at my y coordinate there. So now all I got to do is clean this guy up. Well, 4 times 8 is 32, and half of 32 is 16, and it'll be negative, so that'll be -16, plus 2 times 4 is 8. 8 divided by 2 is 4. So the answer to my problem, and it's perfectly allowed when you're integrating, is going to be -16 plus 4, which is -12. That is what the integral between -2 to 4 of 2x minus 4 dx is. The answer is -12. That's because you had more negative area below the x-axis than you had area above the x-axis. So this canceled with this much left over. Okay. Now, drumming those properties into your head, let's take a look at this next guy. This is more of an algebra-ish kind of question about area under curve. So always think integral is area under curve. They're trying to drum this home. They're telling you if the integral between negative 2 and 10 of f of x dx is 14.8, and they're giving you the integral between 5 and 10 of f of x dx is 18.3, you're supposed to find the integral between negative 2 and 5 of f of x dx. All right, so you start looking at this guy. Between negative 2 and 10. Between these two marks, all I'm doing is focusing on the x-axis here. Between these two marks, the total area there is 14.8 square units. But when I go from 5, we'll make this part right here, 5 to 10, the area under the curve between 5 and 10 is 18.3 square units. You'll notice that they're trying to ask you what is the area or the integral between negative 2 and 5 of f of x dx, which in other words is what's the area between negative 2 and 5. Between negative 2 and 5, we're going to call this guy x. The area between negative 2 and 5 is the unknown. And you're going to make an equation out of this as you put the pieces of the puzzle together. So this x area plus this 18.3 area has got to be equal to the total area of 14.8. The total area between negative 2 and 10 was given to be 14.8. The area between 5 and 10 was 18.3. You're supposed to find the area between negative 2 and 5, which is the rest of it. It becomes algebra. So x really does represent the integral between negative 2 and 5 of f of x dx. As I've written this thing out, I'm just using my standard variable x as the unknown here. You can create any letter you want to. So we're going to solve this thing. I'm going to subtract 18.3 from both sides. And 14.8 minus 18.3 is negative 3.5. Therefore, the integral between negative 2 and 5 of f of x dx is actually going to be negative 3.5. There's the answer, and it's kind of more of detective work than anything else. I'm putting the pieces that they gave you together to figure out what was the part that was missing. But areas have to add up, is what this concept's all about. And the last question on this particular section is this one right here. We're going to be getting you guys into integrating this stuff, and that'll be actually the next section up. But they want you to use properties of integrals of how you would evaluate this integral. And it goes back to what you guys did in Calculus 1 with those derivative rules. Integrals are antiderivatives, so the properties have to be maintained. So what the answer to this problem is, if I'm taking two functions, the integral between 0 and 2 of 8x cubed plus 3x squared dx. If I wanted to integrate this guy, just like when you did derivatives, when I did derivatives of functions being added or subtracted, you took the derivative of each one. When you're trying to integrate, doing the antiderivatives of functions being added or subtracted, you have to integrate each one. That would be the integral from 0 to 2 of 8x cubed dx. Keep the same sign, plus, only under pluses or minuses, the integral of 3x squared dx, again evaluated from 0 to 2. Using my properties of integrals, you can, when you're adding or subtracting, you can integrate each term. Okay? And that's actually the answer to this guy. Now, in future sections, and some of you guys may already know this, and I'm going to continue on with this one, but this will be more of the section that follows from this. If I wanted to evaluate this guy, constants always hold over. The integral of an x cubed. Well, when you took derivatives, the exponent used to pop out front and you subtracted one. But being that it's now integrals, you got to do the opposite. The opposite of subtracting one is adding one. The opposite of putting it out front is putting it in the denominator. So the integral of x cubed dx is a formula, which again we're going to be teaching you in the near future. Add 1 over add 1. That'll be x to the 4th over 4. And then we're going to put this little bar, evaluated from 0 to 2, because it's going to be a numerical value. So once you integrate it, you clean them up. Plus, 3 is a constant, hold over. What's the integral of x squared? Using the same property of what we call the power rule for integration. instead of taking derivative, putting it out front, subtracting 1, you got to do the opposite. Add 1 and then put that number in denominator. Add 1 to 2 is a 3, so it'll be x cubed over that same power 3. Again, evaluator from 0 to 2. This cleans up 8 divided by 4 is 2, x to the 4th. Evaluator from 0 to 2. And then here the 3's cancel, that'll be just x cubed. Evaluator from 0 to 2. And then, of course, the last thing evaluating is, and we're going to teach you this about the evaluating an integral, you plug in top number minus plug in bottom number. So this will be 2 times 2 to the 4th minus 2 times 0 to the 4th. Plug in top minus plug in bottom to evaluate it. Plus, and I'm going to do the same thing here, plug in top, that'll be 2 cubed minus plug in bottom, 0 cubed. Plug in top minus plug in bottom into the function you're manipulating. So to evaluate this integral, all we got to do now is clean it up. 2 to the 4th is 16 times 2 is 32. 0 to the 4th is 0 times 2 is 0. Plus 2 cubed is 8 minus 0 cubed is 0. So this cleans up to be 32 plus 8. So the answer is 40. Again, this question really was what was the property I used to be able to do this. You'd break up over summations or differences. Sums or differences, you integrate each term. That's the property they wanted you to use. But we're again showing you eventually you'll be evaluating these guys. So these pre-section videos are trying to set you guys up for what you're going to be doing in the future. So when you go to class, you're not so surprised by what the professor is doing in class. So the exact area under this particular curve is 40 units squared. So I hope this has been helpful, and I'll see you guys on the next video.